Is my screen visible?
Yes, sir.
Okay, good. Okay, so let us start with the summary of the previous class, as we always do. That we started to look for a certain types of learning problems where we were only given the data points without their labels, and our objective is to group them together in terms of clusters. And this is the essence of unsupervised set of learning problems, which you often encounter in practice, that we need to see associations and need to group them together without telling them what they are, but they belong to same group. That's our objective. So such a clustering problem, since we are grouping it, so we need a very good cohesion in the internal points of a cluster and a good separation among the other clusters points. So depending on that, we first declared certain distance matrix within points, and which should satisfy symmetry, reflexivity, and triangle inequality. And we have also seen some of the distance metrics that we do across clusters, which we sometimes call that average distance, mean distance between 2 points, maximum distance between 2 points, and so on. Then we also have seen some kind of algorithm to cluster data points into different partitions. So we primarily call them as hierarchical and partitional clustering. In hierarchical clustering, we can see that since the name suggests it's hierarchical, so we can do it in both ways. Either we start with taking all of the points as one cluster, and then from top down we cut down the clusters and narrow it further. Or we can start with every point as a separate cluster, and then depending on the closeness of the point or the similarity of the point, we can group them and build the top clusters. So the procedure follows a structured method, we can call structure, which can be visualized in terms of a tree-like structure. We call it as a dendrogram. So, and if we need k clusters, we just cut k minus 1 depth in the tree to get the k number of clusters as we desired in this dendrogram. And depending on the distance that we use intercluster, that is average distance we will use, the distance between the mean of the point, maximum distance between the points we use, or the minimum distance with the points we use, we call it average linkage, complete linkage, and single linkage. So all of them are bottom up, which is agglomerative clustering, and this is widely used primarily rather than divisive clustering, because this is, both of them are recursively implemented, but this is widely used, and both of them perform similar kind of a result in experiments people have shown. However, this kind of approach suffers a drawback because of the computational inefficiency, because every point, every pairs of point, pairs of cluster distances need to be computed, and it is very much sensitive towards noise. So that's why people also try for a partitional clustering, which is a k-means clustering is mostly widely used, where we have seen an algorithm of doing k-means, that we start with a given a predefined k number of clusters that we want to divide into these points. We start with k number of buckets, and we have start from arbitrarily chosen certain points inside the buckets, and depending on the proximity of other points with this, we keep on pushing the points into this bucket, calculate the mean, reformulate the bucket once again with respect to the points that we have, calculate the mean, again reformulate the buckets, until and unless we proceed this way, until and unless we get the previous iteration and the current iteration produces the same bucket values of points. That means it is not changing anymore. So we converged there and say that these are the number of final clusters we can answer. One particular point that we miss to tell is that since single linkage, if you look at this single linkage in more details, this algorithm, single linkage clustering. So as you know, it uses the mean distance, whereas this uses the max distance and this uses the average distance. Since it uses a mean distance between the points and try to group it like as we do it bottom up in the dendrogram. So in computational parlance, it's just finding a spanning tree out of it, isn't it? Because if you are given a cluster of points, what you do in Kruskal's algo, if you try to remember the Kruskal's algo of finding minimum spanning tree, what you do, depending on all possible edges or the distances that we have, I first choose the minimum among them to be the first, then the next minimum. In this way, I just create a tree like structure among these set of points I have. Sorry. Among these set of points that I have. Let's try to do it a tree like structure. And finally, when the number of clusters that I need, those many k, if I need k number of clusters, finally k minus 1 number of edges I have to cut down. So I cut down those maximum or heavyweight edges in from this cluster to produce this many number of clustering. So it's just a minimum spanning tree algorithm, primarily the Kruskal's algorithm. Those who have done an algorithm course or a graph theory course, they can understand that a minimum spanning tree is a spanning tree of a graph. That means spanning tree over a point where there is no cycle and the edge weight sum is the minimum. So we start with minimum and then keep on doing it until we find a cycle. We do not put that. And finally, when a full tree has been done, then starting from a maximum edge, we just cut it down k minus 1 number of edge to get the k cluster. So that's the implication of algorithmic implication of single linkage clustering. So in today's class, we will also see, since k-means algorithm has certain drawbacks, though it is computationally very efficient, as we have seen in the last class, and it converges very fast, it is robust to the noise and outlier point. But there are some drawbacks that it has, as we have pointed it, that the center of the point tends to be dragged towards an outlier and misclassifying that outlier into a partition. So instead of that, if we could create partition with respect to density, as you can see that suppose a point is far away, somewhere here in this clustering. So what will happen, one cluster will get dragged and your center, as your center, you can see one center is here, this I can get, and one center is somewhere here. Due to this point, the center may be getting dragged and some of the points may form cluster with this. Later, we need to, as we have seen, we need to have additional strategies to divide and find which is an outlier and all. Whereas if we look at the density of the points directly, we can find out that the dense points together would make a cluster. Can we formalize this and produce a new kind of a partitional clustering, which is density based, that is very much needed to detect an outlier. So that we will see in today's class, and also a little bit of evaluating which cluster is good than the others. So with that, let us start, which is called a density based clustering. So what we do is we draw a certain set of points first. Suppose we have a point like and let's say they have some outlier points. Now, as you can see that if I go with the density, it is an obvious choice that I may group this, and I may put as an outlier as these two things. However, in k-means clustering, there is a tendency that to put these 2 points inside a certain cluster. So since I am looking for a density, so that means I need to first determine whether a point is within a dense boundary or not. Whether a point is within a dense boundary or not. That is my first consideration. So with that, we declared something as dense points or core points. So the definition of these goes that if a point xi is said to be a dense point, if I draw a circle around that point, with an unique radius, and if I found that there are more number of points than my allowed points, so suppose I allow certain kind of MP number of minimum points to be residing within this circle. If I found that the circle that I draw over with this point xi has more number of points than my allowed limit, then I call this is a dense point because it is surrounded in a dense population. So you went in a railway station, if you are surrounded in a dense population, that you can understand because the number of people around you should be more than certain predefined threshold. So we call such points as dense points. So obviously, with respect to dense points, there is a chance of forming a cluster. That's why we define such thing. Accordingly, we need to, so since we need which points will be inside a cluster, we also try to find out the borders of it. That means the points that belong, not that may not be dense, because if you draw a boundary within this, that may not be dense, but that can lie in near to the border. So we need to also understand which are the points which are my border points. So border points are those points from which any core or dense point is within a particular boundary or threshold. Okay, border point are those points. So suppose xj is a border point and xi, I know that xi is a core point. So it is within some threshold that is also predefined. So this is predefined and this is also predefined. Now I call these points as my border points. So to give you a pictorial example, suppose this is my circle and this is a point which is xi, I call it as a core. I call it as a border point if this point lies this my allowed epsilon, and within that epsilon a core point falls. So all such points which lies within a predefined boundary from a core are my border points. And remember, this is a circle since we are considering two attributes. It will be a kind of a sphere if we consider three attributes. It would be a kind of a hyperbole if we consider multiple dimensions. So we can just extend it generically. Apart from these 2 points, which are dense and which are core, all other points, that is the outliers like this, I call it as a noise points. Okay, this is as per definition because I can just define it this way, but we need an algorithm to go through these points and make the clusters ultimately. That's what the role of clustering or unsupervised learning is all about. But to make my algorithm or to make sense of my algorithm, I just declared 3 things. One is dense or core points, border points, and which are not border or which are not in dense region, they are noise points. So these are my basic definitions through which I will try to design my algorithm. So now see that I have to define something called connectedness, because I say that this is dense points, so there are many nearer neighbors that are connected. Some border points up to which I will connect a cluster and try to form it up to border points. So I need to define something called connectedness. So so connectedness will be a recursive definition. As you can see, with respect to these things we have, we can easily define it recursively, which the base condition would be core points. Suppose xi is your a core point, and xi is directly connected to a point xj, meaning that within a circle, within a radius, if I find a radius where there are this MP factor threshold satisfies, the xj, all xj points are directly connected to core point. So this we say directly connected. So given a core point, I draw a radius, and in that radius, obviously that radius will have this more than minimum number of point thresholds I have. So all the points that comes inside this radius are directly connected to my core. So obviously you can understand that with respect to epsilon, if xi is a dense point, then this relation also holds. So these are symmetric. My definition of directly connected and this formula is symmetric. Now what can happen? You see, now how can I find the frontier of this set of dense points up to the boundary? you can easily guess by recursive formulation that if xi is connected to xk1, xk1 is directly connected to xk2, xk2 is directly connected to xk3, so on up to xkm, which is directly connected to xj. Then recursively, I will say that xi is also directly connected to is also path connected to xj. Sorry, this is called path connected. So which means that if I draw a circle in xi is a core point. If I draw a circle in xi, xk plus 1 comes in. If I draw a circle in xk plus 1, xk plus 1 it has a dense, within that dense boundary, I have xk plus 2, and so on recursively. I can define that my cluster will span from xi to xj because xi and xj are path connected. So with that, again with these two definitions, that one is what are the definition of core point, border point, and dense point. Secondly, I define what is called directly connected, and thirdly, a recursively path connected component. I am now in a position to declare my algorithm. So first of all, the algorithm step A would be all points that are path connected from a core point form a cluster. Obviously, this path connected definition, you can understand why. Because by this, I am going like this, forming a chain of points and saying this to this is path connected means if this is dense, this is dense, this is dense, this is dense. So obviously, this is forming a cluster. So therefore, the step A, what I have to do is that all points that are path connected from core points form cluster. But remember, this is a recursive step. All points that are path connected from a core points means you need to find which are your core points first of all, and you need to find a path connectedness logic which is recursively drawn, and to find all possible points which are path connected from the core points. It gives us an immense opportunity because at step B, now you can see here that these points are no use, right? So it gives an immense opportunity for outlier detection, because our whole principle is based on dense points. So this algorithm that we just discussed is called DB-scan algorithm. So the full form stands as this, that it is density based spatial something. I mean, I just forgot, spatial clustering of spatial clustering and of A is for application of in noise. Density based spatial clustering for application in noise. This is a DB scan algorithm people do. But the primary drawback this has is that it cannot be applied to higher dimensionality. Can you tell me why? What will be the problem if we try to apply in higher dimensionality? Dimension means the number of attributes. If there are more number of attributes, it is very difficult to apply.
So distance calculation will be costly, and we have to calculate distance between every point.
Yes, see what we are doing. We are trying to find a distance and go to find a path, right? From every core point, you need to find a path. And now see, if it is a dense cluster, then this point is a core. This point is also a core, because if you draw another circle around it, this will also satisfy this formula of minimum points in the threshold. So there will be many core points, and for many core points, you need to find all these path connected components to find the boundaries of it. This is computationally very inefficient, and therefore it is primarily used in spatio-temporal data sets where the attribute space is much less. And the second problem it figures is that the whole algorithm is primarily based on density. So if your point densities are of very arbitrary nature, for example, suppose I have like this one cluster, and suppose another cluster looks like this. So now see, what I was trying to make here is, I was trying to make one cluster like this and another cluster like this. Now, due to the density only I am considering, you see, there is a chance that this will be path connected. You do not have levels. You do not have this orange and blue. Every point is same, right? So depending on the distribution and the density, it is very difficult, but it is very much popular in finding outliers. As you can easily understand, outlier will be far away from the dense point, right? So as someone pointed out, what happens if a point is an outlier? This algorithm is primarily used for that. Okay, any further questions?
Yes, sir. I have one question.
Yeah.
Sir, for when we are determining the path connected form xi directly connected to xk1 and this type of things, then are we considering all the points within the cluster and make a MP radius circle in this way, or just within few we are considering?
No, what we are considering, see, if xi is directly connected with xk1, meaning that xk1 will be less than epsilon radius boundary of xi, right?
Yes, sir.
Then we are seeing whether xk1 is directly connected to xk2. Similar formula holds that this distance will be less than epsilon. Okay, so that's why I told you, first we are trying to see this kind of a frontier, then we are extending the frontier this kind of a thing, and then moving on.
Yes, sir.
So that's why this kind of arbitrary shaped cluster it can form. But here the problem was, in arbitrary shaped cluster, it was that it was so intermixed in between that I cannot find the boundary. These points will also be my core points. That's the problem.
Yes.
So as it is a density based, so if there is no clear segregation, it will be difficult. Otherwise, if there is a clear segregation of the classes, it is very easy to use this with a less attribute. You will get absolutely good arbitrary shaped classes.
Okay, sir. Another one question is, when we are considering suppose x1, x2, x3, three dimension or something else, then why we can't use a sphere instead of a circle? And then
No, that's what I told. In 3 dimensions, it will be sphere. In hyper dimensions, it will be kind of a hypersphere or a ball.
Obviously.
Obviously, that is in 1 dimension. You can see in 1 dimension it will be like this, a particular interval from A to B. In 2
Yes,
dimensions,
sir.
it's a circle. In 3 dimensions, it's a ball. In 4 or higher dimensions, it's a hypersphere.
Then this algorithm will be complicated for
Yes, because
calculation.
every core points you need to compute this. For every core points, every path connected components you need to figure out like this way, which is time consuming.
Okay. Yes, sir. I got it. Thank you, sir.
Yeah.
Sir, excuse me, sir. So how do we? So what are dense points basically? How do we select those dense points
Oh,
initially?
that yeah. Selecting those dense points will also you have to consider, let's say you have n data points. For each n data point, you just build a circle with radius epsilon and try to figure out if the set of points within that circle is more than your threshold number of points. Then that is a dense point. So you have to iterate this process for all n's.
Okay, sir.
Think if you can make it better. There are algorithms which make it better, but not in the worst case. Okay, but there are, in average case, it can make better. Okay.
So how do we like know this epsilon value like before?
No, this is dependent on user's choice, and you do it and try to evaluate the cluster. You do a different epsilon, try to evaluate the cluster. Get it? You have to validate what you get.
Okay.
You select a epsilon, get a cluster set of cluster. Then you select a different epsilon, get a different set of different cluster. Though the number of clusters be the same, but a different orientation of the cluster. Now you have to evaluate between these two orientations. As we have given you for the project also, you can see that different orientations of the cluster may result different values. I will today I will exactly point out one evaluation matrix that is you will be using in the project, and also that people use widely. So one is the scatter coefficient, which says the cohesion versus separation factor, but it is not too indicative. Today we will see a silhouette coefficient kind of thing. Okay, so these are primarily what we follow in terms of making a point into separate clusters, hierarchical and partitional, and this partitional density based DB scan k-means we do. However, if you can see that all these algorithms are not everyone doesn't have a particular merit, everyone has a merit or demerit to apply. So people also have extended this such things and finding out hybrid clustering algorithms or hybrid clustering approaches, where they tried to use both the flavor of partitional as well as hierarchical. Just think how they do it. I'm telling you a scheme. Then we will go a little bit on the steps of the algorithm. Suppose you have the points like this. Now what they do, first they try to have a high value number of clusters, a high value of k first they take. So let me just start writing the steps also. So they first try to cluster all points with a partitional clustering. Let's say k-means. I apply k-means. With a high value of k. Then what will happen if there are more number of baskets to have a very high value of k, then essentially this type of groupings will happen. Right? If I have a high value of k, isn't it?
Yes, sir.
So now you can see the essence at the second step, after partitional has done, with the bigger clusters, I have a k dash, which is obviously a far more less than k, and do an agglomerative clustering with k dash as final set of clusters. So which means that with this now I have my points are these big points are now in my hand, and I just go on applying my hierarchical clustering algorithm. And as you know that if I want 3 clusters, I just cut it here. If I want 2 clusters, I just cut it here. And if you want 2 clusters, essentially this will be formed. So this algorithm, since it uses both the concept of partitional as well as hierarchical, we call it as a single linkage k-means. And in colloquial machine learning terms, you will see this algorithm is also called a Clara algorithm. Okay, so this kind of hybrid approach, I am just showing you one such hybrid approach. There could be many such hybrid approaches possible, and you can also try to implement, if you have free time, you can try to implement with different sorts of these approaches, because then you will get both the benefits of the drawbacks of partitional clustering as well as the drawbacks of hierarchical clustering will be somewhat nullified. So with that, we just, since we saw a different kind of a cluster algorithm, so let us try to figure out experimentally what is our goal when we go for the experimental purposes of clustering. So during experimental clustering, what we do first, your first bottleneck is what is the value of k. So then you looking at the data points, if you cannot plot it, I mean, in this 2-dimension or 3 dimensions, you cannot plot an arbitrary number of dimension points. So you just need, with respect to a domain knowledge, you just have to assume it. So for example, it's within a threshold from A to B, you just have to try out from this number of clusters that you get. So you may get 3 clusters, you may get 2 clusters, you may get 4 clusters, and among them you need to compare, number one. And number two, with respect to the parameters of clustering, as in the previous class Deepak was trying to say that what happens if I choose these parameters different. So therefore there is also another thing, that parameters, or sometimes we refer to as hyperparameters because it's a high dimensional class, hyperparameters choice. Then you will get similar set of clusters. However, your clusters may look arbitrarily shaped. Right, your clusters may look arbitrarily shaped depending upon these choices, and now you need to evaluate. So finally, where we reach here is, for the better selection of this and for the better selection of this, is the question that how do we evaluate clustering solutions, that whether this type of clustering is good or with respect to this or with respect to this, or whether this type of clustering is good or with respect to this or with respect to this. So one of the metrics we saw is as a scatter coefficient, but it has many such small theoretical challenges, as someone will also point out. But what we use is called Silute coefficient, and I will try to explain it in details because that will also be needed in your project. So the role of clustering is primarily to find out the cohesion in the data points of a cluster and the separation across clusters. So let's say pictorially, I have this as my cluster Ci. Okay, suppose there are m number of clusters, C1, C2, Cm. This is a cluster, and suppose there is a point I, and with all points j inside the cluster, first I try to determine the cohesion. Cohesion means how well these are connected. So to determine it, obviously I need to call my distance matrix, because the distance is the dissimilarity between the points. The higher the distance, the less these points are similar. So hence, I will try to dictate for every point in a cluster Ci. For every I, we call it for all I which belongs to Ci. I try to write such kind of a metric, that the cohesion I will try to say is that it's summation of Dij for all j belongs to Ci, where j is not equal to I. Right? So that means that I sum all the distances, and then finally I take an average over the number of summations I made. I made Ci minus 1 summation because of j not equal to Ci. Get it? So this is kind of a dissimilarity index. So I mean, cohesion is, I just want to point out that we are measuring cohesion. It is basically a dissimilarity index, as you can see. Right? Isn't it?
Yes, sir.
Yeah, and I mean, you can also call it a similarity also if this you proportional it to 1 by s. Right? I mean, if you take s here, the similarity index, it will be 1 by d. So it is also it will be the cohesion. So what I want to mean that you can easily change it to cohesion by just saying it, instead of dissimilarity, I take the similarity index divided by 1 mod of Ci minus 1. So let's say this be my AI. The similarity. Let us make it the similarity or the cohesion thing intact. The other thing what you will measure is that suppose there is another class CK. There also I have some point J. Then I need to measure which is called the separation index. So to measure the separation factor, I need to also see the distance here between these 2 points. So let's say Bi for point I. So for all I in a cluster, first of all, I measure this. The Bi is basically all the points that are here. I do a sum of the distance from I to J, where you know that J belongs to CK clusters. And how many of them I did? This many. Right? This is the average or the mean separation index for a point I with respect to other clusters. With respect to one cluster CK, let's say not the other all, with respect to one cluster CK. Right? Till this point is clear?
Yes, sir.
Now I declared something called a silhouette value of point I. So silhouette value of point I, let's say call it SI, is what is given in your project document. It is Bi minus AI divided by max of AI and Bi. Let us try to understand this. So to understand this, let us try to break it down to 3 components. One is when Bi is far more than AI, when both are same, you can easily understand this will be equal to the 0. And the second one of interest is Bi is far less than AI. Right? So when this happens, you can see my SI will be equal to when Bi is far more than AI. So obviously this max will result Bi. So Bi minus AI divided by Bi is minus this. Agreed? When this will be the case, then my SI will be, AI will be maximum from here. So Bi by AI minus 1. And obviously in other scenarios where Bi equal to AI, this becomes 0. And or in the other cases where I have only one point, so there is no point of measuring distance. I just, so when I have only one point, or rather this Ci is equal to 1, then obviously I say my Si equal to 0. Now you can see that depending on these factors, I can say that Si value ranges from -1 to 1. Agreed? Because see, if Bi is very much, then this term will be 0, Si will be 1. If AI is very much, then this term will be 0 and Si will be -1. Yes or no?
Yes, sir.
Yes, sir.
So what does this -1 suggest? If I tend towards -1, it means that my AI is far more than Bi. Right? Yeah. So what does it signify? What was my AI earlier? If my AI with respect to the distance, if I take this AI with respect to distance is far more than my Bi, which means my cohesion is bad, right? My cohesion is bad. And say it was not that good separated as well, because Bi is very less, AI is very high. That means AI is this one with respect to distance. So my cohesion is bad and Bi is less. That means this point should not be in this cluster, but should come in here. Yes or no?
Yes, sir.
Just think of this factor. AI is the distance. I am not talking about the similarity. Just forget this. It was an illustration. AI is this. If AI is high, that means the cohesion is bad. BI is less. That means this point is tending towards here. BI is less means it looks like I want to be in the other cluster. So towards -1 means your clustering is not that good for point I. For point I will define for everything. For point I, it says this. Whereas if this side is the case, your BI is very high, AI is less. That is desirable because BI is the factor that separates out AI from the other class. Right? So that means
Yes,
if
sir.
it is in this side, so your ith point is in good shaped cluster. It's in proper cluster for say. Somewhere in the middle, you can see somewhere in the middle when SI is 0, I mean BI, AI are almost similar. Okay, not exactly it is 0 if both are same. That's the case. But if they are similar, then this point is somewhere in the middle of the center. You can see because I am saying its separation and cohesion are equal, which means that I mean ghar ka na ghat ka types. I mean it's not in CI. It may be in CK. It may be in CI like that. So therefore, if we are tend towards -1 or +1, we have a hope because +1 we do not have to do. We are in a good shaped cluster. If we tend to -1, that means that we need to do something better. So both are indications, but 0 is very, very bad because 0 means that, I mean, where should I go into? So obviously, when I get a 0 also, I need to change of the cluster dimensions, and sometimes we need to bring in a cluster in between these points and all. Now, what I will try to do is, depending on, this is for one point in CI. Now for all, I need to go for all points in CI. So for all I belongs to CI, I have this SI. I computed SI for them. Now, if I go from one point to all, I need to compute something is the mean of that class. So all the silhouette values that I compute, this is a mean of all SI. I denote it as an S tilde I. Now, finally, you need to give one coefficient as the silhouette coefficient. So people used to give the silhouette coefficient of all the classes as the max of K, this one, which has the maximum value of this coefficient K. And obviously, the maximum value, people take a mod of it. I mean, when they do it, they take a mod of it because if it is towards 1, I am good. If it is towards -1, I am bad. But both are good indication of this. And often we will see that this curves follows a bell-shaped or a Gaussian distributions in practical scenarios. And then I mean, if we are 10 towards 0 here in practical scenario, then we need to change up. I mean, if it is the curve is like this, the most number of points are tending towards 0, then we need to do something again, iterate and try to find a good cluster. Clear silhouette coefficient concept. So that's why you can see this formula we have given to you in your project, but just we have given B minus A by max of B comma A. In your project, you are seeing that this is your scatter coefficient, which is basically a silhouette coefficient.
Sir, can you repeat this last part again regarding silhouette coefficient?
Yeah. So what I did, see, I is for one point in a cluster CI. I compute this silhouette value, SI, right? I compute this silhouette value for every point. Then the
Yes, sir.
mean of every point, I just denote it with S bar I. I mean, all the silhouette values that I computed, the S bar is the mean of all the points for this cluster I. Okay. Similarly, here also I have a mean of this cluster K. Some other cluster J will also have a mean this, right? Now, finally, the silhouette coefficient of your clustering. That means, see, you give K number of such, M number of such cluster. So I need to give one coefficient value. So this has S1 bar, S1 tilde, this has S2 tilde, this has SM tilde. I take the maximum among them as and give the silhouette coefficient is this. So if you take just the maximum, see, tending towards 1 is better, right? So if you take the
So,
maximum,
sir, by S tilde of I, we mean S tilde of cluster I, like CI,
yes,
right?
yes, yes, yes.
Yes, sir.
So this is what the Silhouette coefficient is all about, and you can understand from the analytic perspective that why we need it to be tending towards -1. That's why we take a max is the Silhouette coefficient, how good or bad you are. You can also play around with it. I mean, this is not a fixed. Silhouette is one type of coefficient that experimentally has been seen. If you take a max, it results good. You can play with this max as well. You can take an average of all this and all that. Okay, and depending on the distribution of the data, people sometimes take a certain probability distribution to find out this. I mean, not a particular max, mean, or average something. Okay, there are different names of those kind of coefficient, but Silhouette is experimentally proven to be very good.
Sir, when we are considering the separation, which cluster we are considering as CK?
Here, CK
Yes.
is the neighboring cluster. So what I will do here is that your CK that you finally get it here is the neighboring cluster. So this a very nice point. I missed a point. This I want to mean.
Okay, sir.
Yeah, everybody please note, I just missed a point while telling. I told it that it's a neighboring, but equation wise it's that CK which is your neighbor, which is your neighbor. I want the separation from my neighboring cluster.
Okay, sir.
Okay, and I would suggest you
Okay.
to read this from Wikipedia once, and there is also a link. I mean, I'm just showing you. This is very nicely projected. Some things are, I mean, when it's of mathematical nature, this Wikipedia Silhouette clustering is projected very nicely. That's what I missed. This is the mean. Okay, so it is very nicely thing, and the other things that we are doing that determining the number of clusters in data sets. If you read those, you will get the other types of extensions from Silhouettes. Okay, and as you can see, the reference is from applied mathematics. So it's a mathematical or statistical concept that has been adopted here. Above all, common sense with backed up with mathematics. So I would not like to go into another new topic to start with, but this I have to do it a little bit earlier rather than finishing off our traditional supervised learning, because you had a project in your hand. So with this background, I hope you can now conduct your project. But next, I will again resume a little bit from the previous supervised case once again in the next lecture. And what we will try to see is that instead of we are always trying to figure out that one type of learning algorithm or one type of learning approach and try to find out the parameters of it or try to make it polished more and more. There are alternative approach of learning that instead of only using one type of hypothesis to find out and fix it, we can learn different types of hypotheses. For example, different types could be one decision tree, one neural network, and everything. And all the hypotheses may not perform good on every set of data points. So how can we assemble these hypotheses and try to reason out based on a majority the appropriate learning outcome? That will be a very nice topic to ponder upon. So since we have a decent background now with all the supervised techniques in our hand, so we will try to figure out small learners which are called weak learners. They may not be good in the over entire data set, but they are good in the small fragments of data set, and how we can compose them, or rather in machine learning terms, we can ensemble them to find out a better learner. So that we will again go back to the supervised learning domain in the previous class, in the next class. So up to then, this is what we require for your project. And obviously, we use this kind of a clustering primarily to detect outliers and sometimes to detect uh, the types of head speeches in Twitter, sometimes the extreme weather condition as an outlier, or maybe sometimes certain kind of a grouping. If you look at our the the slide that I put up, at the last you might find one particular figure. I just put it upon you because it's very interesting to know the background of that figure. So just go through these slides. These are more, I mean, since I do it by hand, my handwriting may not be as good as this kind of a pictorial thing. Can anybody tell me what does this signify? Are you able to see the screen?
Yes, sir.
Anybody has seen this earlier? This has a meaning
Apple
with respect to
symbol.
clustering. No, apple symbol and the left one.
Google.
The
I think.
clustering
Google.
of the
Google.
sheets.
But clustering of what? I mean, it looks like a
Sheets.
clustering, but clustering of what?
Clustering of sheets of the apple mainly. I think so.
So it has to do with the companies as well. So this is how the product teams, I mean, work together to design the product. What are the core teams? How they interact with that cluster. Okay, and
Oh.
the reason is that in Apple, see, Apple has a very few products with a very high impact. If you realize, see, Apple Watch, MacBook, this and that. Google has a large set of products. See, Gmail, in Gmail, you will have different types of filters, labs, all of from a different groups, right? Google Classroom, Google this Gmeet and all that. So there are many such groups working together and forming a small clusters, these black holes, and the depth of the black is the number of people working in that. Google Earth is something, Google Map is something, Google Street View is something. So this means that Google has different, I mean, diverse natures of product teams that are developing up, and this is how Apple works. You may search that this is a very popular figure that came out. Anyway, let me stop here. I think I have spoken enough with clustering, and I hope you can do the project with this. Any questions you can ask.
Sir, in the assignment, for the final salute coefficient, it is given to use the mean of all the salute values. And
Yes, I said
so
no,
which
this
one to
max
use?
one. No. You use what is written in the project. I said it's max one. You can use a mean also here. You can use a mean in
I mean the
of
average, sir.
Yes, average of all salute values.
Also, so this salute values, this depend on the distance matrix which we use in the assignment. First,
Absolute.
for
Cosine
clustering,
similarity.
we are using cosine similarity, but for this computation, do we need to use Euclidean distance or the inverse of cosine similarity?
No. Inverse of cosine similarity as a distance matrix.
Okay, sir. Thank you, sir.
Okay. Yeah.
Yes.
Okay, so Anusruti, you just joined late. You will be taking the scribes along with Sontu.
Yes, sir.
Okay, thank you. I'm stopping my recording and